So we know that momentum is conserved in any collision, regardless, as long as we have an isolated system. And so if we put the objects close enough together, um, we can consider any system to be isolated just before its collision. So during any collision, momentum is conserved. If we look at just the instant the collision occurs. So what I want to talk about in this video is a special type of a collision. There are two types of collisions that we'll cover in this course. They are perfectly elastic collisions and perfectly inelastic collisions. Now, elastic, like a spring, it bounces back. You hit it and it bounces back. So inelastic would be the opposite of this, in which it would not bounce back. In a perfectly inelastic collision, the masses stick together. So we have here, so we have this collision. We have a before picture, which we have a mass of m coming along at a velocity of 1, and we have a mass of 2m, it looks like, which is initially at rest. This velocity is equal to 0. When they collide, this mass, maybe this is a clay mass or something like that, and this is a harder ball there. After the collision, this clay will stick to this other mass, and of course when it hits it, it's going to make it move off its velocity, some new velocity. They denote it as v prime. We'll denote this as v final. Okay, so in a perfectly inelastic collision, the objects stick together. This is the definition of a perfectly inelastic collision. As you'll see in the next video, perfectly elastic collisions are ones that bounce off of each other perfectly. The reality is that there are no perfectly inelastic collisions or any perfectly elastic collisions. Everything is somewhere in between. We call it partially inelastic, is the reality of collisions. So real collisions are partially inelastic. But we would need to know exactly how inelastic they are or how elastic they are in order to make any calculations. So we're not going to discuss them very much. We're going to look at two extreme cases in which, some things do kind of fit this bill. Let's say we have like a clay ball running into something much harder, and they stick together. That would be, we could consider that to be perfectly inelastic. So the conservation of momentum for a perfectly inelastic collision, we have here our before. So we have the initial momentum will be equal to, and I'll call this is object A, and this is object B. The initial momentum will be the mass of A times the velocity of A plus the mass of B times the velocity of B, all in the initial condition, right? And the final momentum is this here. We have final momentum is going to be equal to mass of A, velocity of A, plus mass of B, velocity of B, in the final condition. However, since these are stuck together, they must have the same velocity. So we can write the final momentum as the mass of A, factoring out, knowing that VA final is the same as VB final. Then we can factor this out, and we say that the final momentum is the mass of A plus the mass of B times their shared final velocity. Okay, so our conservation of momentum for a perfectly inelastic collision looks like this. We have mass A, velocity A, plus mass B, velocity B, initial is equal to mass A plus mass B, times their final velocity. This is conservation of momentum for a specific case, in which case we have a perfectly inelastic collision. Okay? An important thing to note with inelastic collisions, though, is that there was some energy associated with mass A here, right? It had some kinetic energy. There was some kinetic energy here, right? So there was some kinetic energy associated with this. This one was at rest, so its kinetic energy was equal to 0 in this case. When the clay mass, mass A, collided with this other mass, mass B, then in order for it to stick to it, it needed to deform. And actually there's probably some sound made as well, right? So when this deformed, there was some heat generated and there was some energy that was consumed, some mechanical energy which was consumed in the process of that collision in order to deform the clay. So in a perfectly inelastic collision, the kinetic energy is not conserved. So that's very important for an inelastic collision. So kinetic energy, or actually the change in kinetic energy, is not equal to 0. So there is a change in kinetic energy. Okay? If you look at this next figure shows that. We have a before picture over here on the left. We have an after picture over here on the right. And the momentum before, so we have a mass of m. Both of these are actually mass m. So mass m here. If we look at the initial momentum, this is going to be the mass of A, which is m, times the velocity of v. I'll call this, actually they've already described this for us. Positive is to the right and up. The first block had a velocity of v. The second block had a velocity of negative v. So we have mv plus m times negative v. So the initial momentum is mv minus mv, which is equal to 0. It had no momentum to begin with. The total momentum of the system was equal to 0. So then the final momentum, which we know because this is an inelastic collision, they've shown them stuck together, so this is an inelastic collision. The final momentum is the mass of A, which is m, plus the mass of B, which is m, times their final velocity. And so, since the initial momentum, in any collision, we have initial momentum equal to the final momentum, we must have 0 is equal to the mass, the two masses, so this would be 2m times the final velocity. Because the mass is not 0, then the only thing that can be equal to 0 is the final velocity. So they have come to a rest, which is exactly what we would expect. If we have two masses going in opposite directions at the same speed, and they collide and stick together, we would expect them to come to a rest. They had equal amounts of momentum, but in opposite directions, so the total momentum is equal to 0. However, if we look at the kinetic energy, if we have, let's take a look at the kinetic energy before. So KE initial. And now kinetic energy is not a vector, right? So when I add up the kinetic energy of the system, this is really the kinetic energy of A. This is the kinetic energy of A plus the kinetic energy of B initial. So this is equal to 1/2 mass times v squared plus 1/2 mass times negative v squared. When I square this velocity, it becomes negative v squared is the same as v squared, right? The negative turns to a positive. So this is equal to 1/2 mv squared plus another 1/2 mv squared. This is just mv squared. That was our initial kinetic energy. Now our final kinetic energy is going to be 1/2 of twice the mass times the final velocity squared. But we know from conservation of momentum that the final velocity is equal to 0. So our final kinetic energy is equal to 1/2 times 2m times 0 squared, which is equal to 0. So in the initial kinetic energy, we had mv squared. In the final kinetic energy, we have 0. All of the kinetic energy was lost. Now, not lost like it's gone forever. Energy is still conserved, but mechanical energy, and very specifically kinetic energy, is not conserved here. So what happened to all of this energy? Well, during the collision, sound was produced. Sound is a form of energy. So some of that kinetic energy was transferred to sound energy. These blocks heated up. There might have been a little bit of deformation. In order for them to lock together, they'll need to deform a little bit and lock together. So the kinetic energy went to heat, to sound, to deformation, etc. So inelastic collisions, ones that stick together such that the initial momentum of the system is the final momentum. This is just conservation of momentum, but it simplifies down very nicely because in the final condition they share the same velocity. But kinetic energy is not conserved, so energy is lost during that collision.